Here's one problem where I can't really draw a picture, so I just have this XYZ coordinate frame. We have the electric potential given as a function of the coordinates x, y, and z. If you look at this expression carefully, you will see that the electric potential depends on x, it depends on y as well, but it doesn't depend on z, and capital A, B, and C are just constants. In part A, we are calculating the components of the electric field vector in this region of space. Now, how do I go from electric potential to the electric field vector? I need to take partial derivatives, like so. The x component of the electric field vector is equal to the negative of the partial derivative of v with respect to x. So let's go ahead and take that partial derivative. Now, when we take a partial derivative, we treat everything other than our variable, in this case that's x, we treat everything else as constant. So I know that y is another variable here, but when we take the partial derivative with respect to x, we will treat y as a constant as well, just like the other constants, capital A, B, and C. So here's the answer. We have the overall negative sign, and then we take the partial derivative of each term one by one. The first term is axy. The derivative with respect to x is simply a times y. And then negative bx squared, the derivative of x squared is 2 times x, so that makes negative 2 times bx. The last term, c times y, it has no x in it, so that's constant with respect to x, so its derivative is equal to 0. Let's simplify this expression. And then we follow the same logic, same formula to calculate the other components of the electric field vector. The y component is the negative of the partial derivative of v, electric potential, with respect to the coordinate y. Again, the first term is axy. The partial derivative of this expression with respect to y is simply a times x. The second term, bx squared, has no y in it, so its partial derivative with respect to y is 0. And the last term, c times y, when we take the partial derivative of it with respect to y, we get capital C. So let's go ahead and write that down. And finally, the z component of the electric field vector is equal to 0. The reason is, as I mentioned earlier, none of the terms in this expression for the electric potential has any z dependence in it. So none of these terms depends on z. That's why when we take the partial derivative of each term, we will get 0 from each term. So E sub z is equal to 0. And here I have my vector E expressed in unit vector notation. In part B, we're looking for points where the electric field vector is 0, and that requires that all the components of the electric field are equal to 0 simultaneously. Now, we know that E sub z is already 0, regardless of the value of x, y, or z, so that one's easy. Next, let's set E sub y equal to 0 and solve for x. Here we have set E sub y equals 0. That makes negative a times x minus c equals 0. And if we rearrange our equation, isolate x, we get x equals negative c divided by a. And finally, let's set the x component equal to 0 and solve for y, and then combine with this result. Here's the calculation. A sub x equals 0. That makes negative a times y plus 2 times b times x equals 0. Rearrange the equation, isolate y. We get y equals 2 times b times x divided by a. Next, we're going to go ahead and combine these two. So I'm going to basically take this expression for x and substitute right here to come up with a value for y. And here's what I get when I do that. Y equals negative 2bc divided by a squared. So the final answer is the electric field is equal to 0 for any value of z, and for these particular values of x and y. So this defines a straight line parallel to the z-axis at x and y coordinates specified here, x being negative c divided by a, y being equal to negative 2bc divided by a squared.